It's a pleasure to introduce Professor Manuel Endres, a leader in experimental quantum science. Professor Endres joined Caltech in 2015 and has been a professor of physics since 2021. He is internationally recognized for his groundbreaking work in neutral atom quantum systems, where individual atoms are trapped and controlled with light, an approach that offers compelling paths toward scalable, fault-tolerant quantum computation. His contributions have been recognized with major awards and honors, including the New Horizons Prize in Physics from Breakthrough Foundation, as well as Early Career Award from the DOE and NSF and a Sloan Fellowships. His talk, Building the First Error-Corrected Quantum Computers, addresses one of the central challenges in the field. Qubits are powerful but fragile, and real quantum advantage will require scalable architectures that can keep quantum information coherent even in this noisy world. Professor Endres' group has recently pushed the frontier of scale in a striking way, demonstrating an optical tweezer array with 6,100 highly coherent atomic qubits, a major step toward the large redundant qubit systems that practical error correction demands. This work exemplifies what Caltech does best: deep physical insight paired with extraordinary experimental ingenuity. Please join me in welcoming Professor Endres.
Thank you, Hirose, for the nice introduction. You almost gave half of my talk already. First of all, thank you for giving me the chance to talk, and thank you for guiding Caltech through also difficult times recently. I hope this will be close to entertaining as the previous talk. I'm not sure if I can match that, but here it is. Okay, all right. So I'll talk to you about a collaborative program, in fact, that targets building the first error-corrected quantum computers that has started some sort of mid-last year. And I think it's a very, very exciting time, and I hope I can convey that. So let me start very basic. What are quantum computers? So classical computers, they encode information in bits, and arrays of bits that you process. And each bit can basically in one or another state. So in a quantum computer, that's different. There we use quantum bits, so-called qubits, and they can be in two states at the same time. And the important part is that this is not just the case for one qubit, but also for many qubits. So if you think about this, one qubit can be in two states, but then two qubits, you can have four states actually. It could be both up, up, down, 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 or down, up. So there's four. So if you do the counting then for many qubits, in fact, true that n qubits can be in 2 to the n different states at the same time. And this is a consequence of the superposition principle and the fact that they can be strongly entangled. And this is at the heart of why quantum computers are so special. So in fact, quantum computers, a single quantum computer, can conduct parallel quantum computing at an exponential scale through this exponential superposition. So in principle, it's a single computer that does very, very massive parallel computing at the same time. And interestingly, in a sense, that's very inherent to quantum systems. So in a sense, any interacting quantum system has this property, but usually it's not as controlled. And this is the reason why simulating such strongly interacting quantum systems like solids or electrons in a solid is actually very efficient with quantum computers, but very hard with classical computers. Because the quantum computer can kind of mimic this massive superposition states computationally. And this is at the heart of this famous quote from Feynman, where he said already 1981, which is was very inspirational at the time. He said, nature isn't classical, but if you want to make a simulation of nature, you better make it quantum mechanically. And it's indeed true. So the best known scientific application of quantum computer is this quantum simulation property, that you can use this massive superposition or this parallel computing ability to study quantum systems, to simulate quantum systems in regimes that are potentially inaccessible to classical computers. And there's a wide range of those problems. It's basically any problem where you have a collection of particles or degrees of freedom that are strongly interacting. And I'm just coming back from a workshop on quantum gravity, of all things, from Stanford, where people now, for example, they devise new models for quantum gravity that could actually be realistic, but they have a very hard time solving them. So there's a new program, for example, to try to implement them on quantum computers, which is just one of such examples. Other examples are non-equilibrium physics of fundamental particles that are very, very hard to study on classical computers, strongly correlated materials, high temperature superconductivity, certain quantum chemistry problems, and so forth. So quantum computers are in principle a very powerful scientific tool. At the same time, they also have commercial application. The most well-known is cryptography. So in principle, with a very good quantum computer, you could crack classical encryption schemes that encode your emails or that are at the heart of cryptocurrencies, for example, or basically any electronic communication. There's also potential applications in the AI space that's a little bit more tentative, I would say. The problem with actually realizing these important applications is that qubits are noisy. So basically, currently, they're too noisy to actually do that. In principle, we have enough qubits and can control them, but they just have too high error rates. And now, how to get around this is to do what is called quantum error correction, or QEC. And quantum error correction and QEC, I'll explain it in a second, is a very important topic because it's, in our understanding, the only way to really broadly address these applications and realize them. So our mission, collaboratively, and I will explain a little bit in detail how we want to do that, is to build the first error-corrected quantum computers and to realize the application potential widely. So this is what we really want to get at. So, and this is important because currently, it's a very exciting time because it's the first time that we could actually experimentally realize quantum error correction. But let me briefly explain how this works. So the basic principles are not that complicated, and if you really want to understand it, it's very hard. But let me just try to get to the point. So the idea here is that you take a number of physical qubits that are just like actual qubits, and then you try to encode quantum information redundantly in a set of those qubits that form what we call an error-corrected logical qubit. So now we have a bunch of those qubits, say like 25, and they encode together a single qubit in a way such that you can actually detect errors and correct for them. So this is the trick. It's basically the same thing as classical error correction, but a little bit more subtle in a way. So, and in principle, this should work, and it has been known for decades that it should work. And in fact, John Preskill, one of my famous colleagues here, is one of the founding fathers of this kind of ideas. But only and these ideas are around for like, decades now, maybe 3 decades or even longer actually. But only in the last year we have seen this experimentally work for the first time actually. And this is very, very interesting because it's in a sense a pivotal moment of the field. And it has been seen simultaneously kind of in work by Google and in work by our new colleague, Dolef Blufstein, I will mention a few more times, who is a worldwide expert actually on realizing quantum error correction with the types of system that we use in our lab. And this is a plot from this work that shows this for the first time working. And I'll kind of quickly explain this. There's a little bit of math, but it's not that hard. So the basic idea is that if you put these qubits together into this logical qubit, you can have an exponential suppression of error. So what's happening in this formula? So there's a basic error rate P for each of these physical qubits, and then there's a so-called error correction threshold. So what this means is that if your error rate of these qubits is smaller than this error correction threshold, this number is smaller than 1. And then if you increase the size of this error-corrected logical qubit, the error rate would go exponentially down with D, which is a measure for the size of the qubit. So that's the basic idea. So now that we're below this threshold, what you will see is that as you increase the size of a logical qubit here from 3 to 5, it's a specific measure, so the actual qubit is like 9 and 25. But you see that the error rate of the logical qubit actually goes down. And this has been the first observation of this type. And it's a turning point for the field in a sense, because now all you need to do, in a sense, all you need to do sounds simple, but what you need to do is reduce P, ideally, find codes where the threshold is large, and find ways where this formula is some sort of the most efficient. Interestingly, now this has been observed in actually 3 different platforms at the level of a single logical qubit. Superconducting qubits, what's pursued at AWS and Google, for example. Ions, that's pursued by various different companies and also academically, and neutral atoms, which is the system that we are using in our lab. And let me just briefly explain how neutral atom quantum computing works, because probably you're not familiar with it. So the basic idea is that you can trap a single atom in a tightly focused laser beam, a so-called optical tweezer. So we take where's the tweezer? That's interesting. So there should be, I'm going to draw it. There should be a tightly focused laser beam here that somehow disappeared by moving it onto this laptop. And in this tightly focused laser beam, we trap a single atom, and each single atom basically encodes a single qubit. Okay, and the qubit you could imagine is, for example, encoded in an electron spin. Factually, is a hyperfine spin, but it doesn't really matter for understanding it. So now we can actually make many of these tweezers, and this is a picture from Hannah's work where we make more than 12,000 of these tweezers using spatial light modulators, as optical engineering techniques, and track about a single atom in each of them. So and you see each of these dots is a fluorescence image of a single atom that each encodes an atomic qubit that has actually extremely low error rates, record low error rates, despite the fact that we scaled up these systems by many orders of magnitude. So how do you do computing with that? So computing works the following. So you have an array of these atoms that are trapped in tweezers. So you see the red dots, the green dots are the atoms. Each has a qubit in it. And now with optical engineering techniques, we can move these tweezers around. So we can actually program movements of each of them and bring them close together, for example. And then we can engineer entanglement locally in proximity. So when atoms are very close together, you can step in a laser beam that excites the atoms to specific states such that they very quickly entangle locally. I'm going to show you a kind of quick video of where this is happening. So this is fluorescence images, again, of individual atoms that are moving around. And then you see when they're close together, you see these nice little red circles. This is when an entangling gate happens. So this is when two qubits get entangled, and we can do this in a very, very structured fashion. Okay, and with these techniques, if you do it right, you can build what is called a universal quantum computer. It means you can program any types of quantum circuit that you want in principle. Okay, it's not just that; it's universal quantum computing with what we call long-range connectivity, and that's very, very special to this system. What I mean with that is I can take one atom from one end of this chain and can move it to the other one and entangle it without having to go through steps of individual qubits in between. It's very, very different from existing quantum computing systems, in fact. And this long-range connectivity plays an important role now in error correction. So now we want to build these error-corrected logical qubits. And it turns out that this long-range connectivity reduces the requirements for error corrections by many, many orders of magnitude. And this is something we found out only recently, in fact, how efficient this can be. So what this means is that if you can utilize this long-range connectivity, you can reduce the number of physical qubits that you need to build one of these error-corrected qubits with very low error rate by several orders of magnitude. And this is unpublished work from Caltech that we are currently writing up for publication. And it's actually very, very surprising how good this can be. And it's something we learned very, very recently. So we have basically what we call ultra-efficient error correction. At the same time, the systems by themselves, they are already orders of magnitude larger than existing quantum computers out there. So we can now control basically 5,000, 6,000 qubits, and we have a very clear path that I'll explain in a second to over 100,000 qubits. And moreover, algorithms with many logical qubits have actually, in fact, already been demonstrated in these systems. See another video of those. Actually, looks a little bit more complicated. So now we do all of these movements, and it's a little bit of an art form. But in fact, it's much easier than you would think. And the reason for that is that atoms are all identical. It's a difference from solid-state qubits, for example. So they're all the same. That means you can easily control them in parallel. And another thing that we learned recently is that in these logical qubits, you do not really need to control each of the physical qubits identically, individually, but you can control all of them in parallel on a block. And not just that, you can control many of those blocks in parallel. So there's a very nice degree of parallelism that you can use to actually make these systems controllable at scale, which is otherwise very, very non-trivial. So there's some sort of a triple whammy here. So first, I think we can be much more efficient in encoding these logical qubits, and that's something we only very recently learned. We already have very large systems, and we know in principle how to do algorithms with all of this. So because of that, we think there's a very clear path to around 1,000 to 10,000 logical qubits with very, very low logical error rates at the range of this encoded redundant qubits. And this is enough, actually, to enable these very broad scientific as well as commercial applications. And in fact, we believe this will come much, much sooner than anticipated. In fact, I thought this was 10 to 20 years away until last spring, I would say, where I changed my mind about this. So this is very exciting. And before I move forward and tell you a little bit about our program to actually get there, I would like to show the video from Hannah, who is very good at explaining these things, maybe better than me.
Hi, my name is Hannah Manich, and I'm a sixth-year graduate student here in the group of Manuel Endres at Caltech. And today I'm excited to tell you about work that our team has recently done demonstrating 6,100 atoms trapped in optical tweezers. These 6,100 atoms can be used as qubits, and this result demonstrates that in the near term, quantum computing at the scale of 10,000 atoms will be accessible. Over here, we have our table where we prepare our lasers at the correct frequencies and intensities so that we can use them to cool our atoms, which are cesium. We send them through optical fibers across this table here over to where we trap our atoms in this glass cell. Our atoms live inside this glass cell here, where they're at ultra-low vacuum pressures. These pressures are even lower than what you can find in the atmosphere of the moon. Here we have an acousto-optical deflector. These devices allow us to pick up and move atoms across our 6,100 qubit array. This is a unique feature of neutral atom quantum computing, that atoms can be connected with other atoms anywhere across the array. And this will allow us to manipulate and control our qubits in ways that allow us to build more efficient quantum computers. Back here is the control system for our apparatus. It allows us to send signals to our experiment, including to the camera, which lets us take pictures of our atoms every single second. Here you can see an image of our 6,100 atomic qubits, every single dot being a single atom that we're holding in these optical tweezers. The scale of this picture is about 1 millimeter across. And the only thing we need to add to make these qubits into a quantum computer is entanglement. That's something that myself and the rest of the team are working on now.
Okay. Thank you, Hannah, for making that video. I think it's one of the most viewed Caltech videos on YouTube by now, actually. So we did this as part of the press release for this paper, but I think they recut it a little bit for you. But I think what you saw here is basically an example of a single PI lab. So that's my lab at the time. And it's labs that are run by 4 to 5 students and postdocs. They're doing an amazing job. As you see, these experiments are quite complicated. And it's interesting that for the specific direction of neutral atoms, these types of labs with a single PI and 4 to 5 students are leading the field. So all the really important work that comes out in this field for neutral atom quantum computing is done in these types of small-scale labs. And so it tells you that they're very good for innovation in a sense, but you also see these experiments are growing in complexity. This is not an easy experiment, I would want to say. And also the associated theory, if you look at these error correction codes, also very, very complex. And the optical engineering that we put into it is also complex. So I would say that what we need to be is we need to be innovative but organized in a way that enables really effective collaborations that go outside a single PI lab to really realize the goals that we have. And then essentially we need a new research model for these neutral atom quantum computers. And we took some inspiration for mission scale observatories and space missions that Caltech is very famous for. Palomar, Keck, LIGO, JPL. So Caltech is really good at pulling off these crazy engineering missions that in a sense maybe have a higher complexity level even than what we are trying to do. So our idea is here that to start a mission-style collaborative project for quantum computing. In fact, we already did that last year. And we have termed colloquially currently Advanced Quantum Computing Mission, short AQC. Again, the goal of this advanced quantum computing mission is very, very clearly defined. All we want to do is build the first error-corrected quantum computers and realize their application potential. So it's very, very direct and very, very focused. And Caltech, we believe, is the world-leading institute for mission-scale projects, as these examples show you. And at the same time, we believe we already have uniquely the right expertise to pull this off. So it ranges from neutral atom quantum computing, where we made 2 new hires recently, Dolev Blufstein, you already saw some of his work, and Tarkwa Opong, Nelson Tarkwa Opong, who is a specialist in precision atomic physics, will help us to scale this system, keep them extremely stable. We have traditionally very, very strong quantum information or quantum computing theory with John Preskill, for example, who is an expert on quantum error correction, but also Robert Huang, who recently joined, who I believe is the worldwide expert for quantum AI, and recently switched gears to a certain degree to work on these quantum error correction codes for our system almost full time, last like half year basically. And we also have extremely strong optical engineering in EAS. For example, Andre Faron has joined our mission to help us out with optical engineering tasks to scale these systems to over 100,000 qubits. So Caltech, we believe, is the best place for this, and the best time is now. And this is some sort of our execution plan. So we have several Pathfinder experiments and theory teams. So this Pathfinder 1 experiment is what Hannah has been working on, where we want to demonstrate this ultra efficient error correction codes for the first time. And in fact, we're following some sort of a blueprint in a way that has come out of this AQS mission already, and this is a patent we filed recently. And it has come out of an experiment theory collaboration, which is this team is what we call practical error correction team, which works on these new quantum error correction schemes in co-design with experiment, and it works on various other aspects that are important. And there's already some results. We have a second Pathfinder experiment that solves a specific problem. In these tweezers, sometimes you lose the atoms and you have to refill them, but it's a non-trivial operation because you have to refill them while not destroying your quantum computer. So this is something that warrants a separate investigation. And the goal of these experiments is already to really show a very clear quantum advantage for the simulation of scientific problems, actually. And in fact, I think we have a very clear route for that. At the same time, we're working on advanced optical engineering now to really do R&D for controlling more than 100,000 qubits with, for example, meta-surface-based holograms. And this will then merge into what we believe could call a quantum supercomputer, if I'm brave, where we would like to really control over 100,000 physical qubits in a system. And this is targeted to go into a new room that will sit in the basement of the quantum the CQPM building, and this is a collaborative lab essentially that's currently being planned and renovated. At the same time, we are already realizing the commercial potential of this technique. So we started a spin-off company very recently that also has a theory team already that already is producing results in collaboration with the campus. And we're planning a first experiment, a so-called prototype experiment that is directly aiming for commercially relevant quantum computer using these techniques. So the idea in the medium term, short and medium term, is for this company to join R&D with campus in particular. It's a bit of a new idea how to do that, to support experiment engineering theory, to have a visitor program, to really spun a collaboration, a theory and experiment, to really accelerate jointly what we call this dual rail approach between campus and the company, a fully functioning quantum error corrected computer development. Longer term, the vision is a little bit that the campus, in a sense, these computers, you can think of them as specialized supercomputers in a way. They can do specific tasks that are pretty important very, very well. So in a sense, you're in a quantum supercomputing business. So the idea is that maybe the campus longer term might be the first places in the world that actually have a quantum supercomputer center where you have quantum computers you can program for scientific applications broadly. And the company hopefully is a leading quantum computer developer. That's the dream here. With this, I would like to summarize. So the mission of this collaborative program is to build the first error-corrected quantum computers and realize the application potential widely. And quantum computers are not just powerful scientific tools that enable you to study scientific problems in regimes that are inaccessible to classical computers, but they also have significant industry interest and societal impacts through, for example, this cryptography story. Anyway, we believe Caltech is the best place for this exciting mission, and we look forward to charting the path together. With this, I'd like to thank you.
Well, if I could, of course, most of us are certainly familiar with the fundamentals of quantum computers using neutral atom qubits. Now, Taylor has a little trouble. So, but I do want to alert everyone that there will be a test after lunch to just make sure that we're all
But we have no problem. There is an error correction algorithm.
That's right. That's how we're going to grade it. But with that in mind, knowing there is going to be a test, if you do have any areas where you're not, really crystal clear on this, here's your chance. So questions?
I do actually have one. But I'm not exactly sure how to ask the question. So you use the optical tweezers to localize the individual atoms.
Yeah.
and then you move them close, and then you use a different laser to entangle them, and then you move them apart.
Yeah, so
and they stay entangled until you measure them, and then they both collapse into the same state, and that's how you do a computation. Is that
in a sense, yeah.
okay?
Yeah. I think it's a pass.
Told you he was a little fuzzy.
Yeah, I can explain the details, but that's basically, normally these atoms are non-interacting at any reasonable distance scale that are happening in these Giza arrays. So you can put them as close together as you can, say micron or something like this, and then if you excite them to very high-lying electronic orbits, they start to interact very quickly. So you can temporarily excite them and de-excite them. And if you do this right, you can tangle them like in a sap. So you can do this very targetedly. And then how the computation works is you move like 2 qubits around, entangle them, and move the qubit away. It stays in a superposition state. There's another qubit. You can entangle it. You can move it around, entangle it, move it around, entangle it. You can do this almost arbitrarily.
So if you have 2 entangled and you entangle it with another one,
then you have 3 entangled, and you entangle it with another one. You have 4
so
forth.
if you entangle this one over here with another one, it entangles this guy over here too.
Yeah. It entangles the guy. So propagates.
Are you clear on this?
Ready to join the lab.
So you're talking about 100,000 qubit.
Yeah.
How many other research centers, establishments are there in the world that has the same aspirations to build to the scale?
Maybe I should rephrase the question. I think aspirations have probably many. The question is how many. So there's a political question. I'm not sure I should answer. I think there's two aspects. So there's how many physical qubits can you have, but the real question is how many logical qubits can you build that are low error rate.
Yeah.
And I do think we have the best plan to go to enough logical qubits to actually reach the application scale. I think that's the key question. And I do think there's some secret sauce in there that's not publicly known, actually, that only we know at the moment. That makes us believe that we can do that. And it's also the reason why we started the company. Like a year ago, I didn't think it's commercially relevant, frankly. But now we're at a time where we believe this is actually around the corner. I mean, you look around and for the first time you see this happening, it's actually very exciting and also a little bit scary to be honest.
So for Caltech, to get to that point,
Yep.
how much money are you talking?
How much of that? No, I think it's like currently we're funding it a little bit with money we have lying around as these kind of things work. If we go to steady state, it's 5 to 10 million a year, which is relatively cheap compared to what people.
For how many years?
We think we can pull it off in 5, but it would be good to have more than that to actually explore the application and have some bandwidth. So can do the calculation.
You got it covered.
I mean, it's much cheaper compared to LIGO in the early days.
That is true. It's cheaper than LIGO, and it's also much cheaper than the programs in industry that people do in the superconducting qubits. And it's the things are efficient in a way that is quite remarkable. And a lot of these components that we use are commercially available. But you don't need to do nanofab or anything. There's some stuff you need to do for 100,000 qubits. I don't want to give the wrong impression, but it's not. There's not specific nanofab required. It's required that you have people that are really good. I think the scarce resource for these types of experiment is not money. Money is a scarce resource for doing it academically. I don't want to get that wrong. But the difficult part is to have people who can actually pull it off, like Hannah. There's maybe 10 people in the world that can build these systems properly, and that's a pretty there's a problem there. So you need to have these 10, 20 people. That's kind of what we're trying to do mainly. We need money too. I don't want
But do you see any physics-related hard problems that need to be resolved before you can get to 100,000 qubits?
The 100,000 qubit control is an optical engineering challenge to a large degree.
So it's not physics.
That's one. Yeah, there's some physics involved in how you do light modulation and so on. And then to do the error correction properly, the thing we need to work on a little bit are the base error rates, for example, for these entanglement gates. These need to go down a little, but there's some work on this already. Actually, there's some preliminary results that tell you we can get them low enough.
Okay.
So we kind of have everything except for some optical engineering we need to figure out, where we have some good ideas.
Thank you.
Yeah, so we have a very clear path, I think.
Thank you.
Yeah.
If I understand correctly, IBM and Google are very close to have working quantum computer of a rudimentary form.
No, it's not really true. I mean, it's true in the senses that they have like around 100
Yeah, very low qubits.
noisy qubits.
And I understand IBM, you can rent time about $1,000 a second in quantum computing. Now, to me, you're correcting error signal. I don't understand how that works, right? Very complicated. But to me, it's like what comes out of quantum computing is a bunch of statistical data. Okay, and then I use it. I got to figure out what is the optimum thing for me to do. So how does your error correction enhance that?
So I think that the key, let me stick back. So if you have 100 qubits that have no errors, it's extremely powerful. Actually, you can do things that no classical computer does. It's very clear, actually. 1,000 is even clearer, actually. And so the current computers, they have, in IBM, they have 100, maybe a few hundred. They claim more, and HANA will have like 5,000, like very soon. Noisy qubits. And you can do something with them, and then for those computers, you can tackle certain problems. In fact, there are some problems where people have claimed an advantage. There's very, very specific problems where you didn't really learn that much. But to really broadly access the applications, the noise has to go down. And the only way to really get the noise down is to do redundant encoding. So even in classical computers, there's classical error correction, in fact, to actually get error rates down. Same thing here. So you take a bunch of qubits together in a way such that it's redundant, such that the joint object can have a very, very low error rate. So that's the trick. So now, to your question of how to interpret the outcome of a quantum computer, if you do it right, it's not that complicated. Because if you do it right, it's the same as programming a classical computer. You just need to understand what is the input, what is the output. And it's only for some problems where the output is some sort of complicated statistical thing. Sometimes the output is a classical thing, like, for example, prime factoring is an example. So you put a prime number in, and it tells you what are the prime number factors that go into the number. And that's very simple outcome. There's nothing to interpret. So if you know the system has low enough error rates, and you can also test the answer. Once you have the factors, you multiply, check it's correct. So there's certain problems where you can check it afterwards that it's correct. So it's not, I don't think it's such a complicated thing in a sense, the outcomes are complicated. The outcomes can be classical answers. You can ask a question, program it, and it tells you yes or no, or things like that. Or it tells you, oh, there's a prime factor thing. Or it tells you, I don't know, so superconductor, I do like a correlated electron system, like a magnet or something like this. And I ask you what's the correlation function. So what are the spins at a certain distance? What is the value of a spin at a certain distance? You can ask these kind of questions and get them out. It's a question of how to program them. But there is a question to that. So even if you have these computers, programming them correctly might be a non-trivial task. So this is why we believe even if you had these computers, you need specialists probably for a while to program them correctly, because there's subtleties in actually doing algorithms efficiently, asking the questions efficiently, that you can really understand the answer. So I think you're getting to the right point in that sense. You need specialists, even if they exist, to program them for a while, for sure. And this is why I think it's meaningful to have those, even if they work in an academic center, also for scientists to use them properly in that way, where you have a bunch of specialists around it that know how to actually use them for your problem of choice. Long answer.
Time for one more. Do we have another question?
I don't understand.
I have a question for Hiroshi. Can I ask a question of Hiroshi?
Yes.
So I took that course from Richard Feynman 40 years ago. And remember thinking at the time, there's no way any of this is going to happen in my life. And now it's going to happen. What is the course in the physics department today that is teaching stuff that students today will say, that's never going to happen? But now, 40 years from now, we'll be going, holy shit.
Well, the last quarter, I taught a course on string theory. If you read this one, there's an article that says that it will take 2,450 years to complete this task.
But this string theory, that's what...
Actually, I'm not sure. These guys at this quantum credit.
But you never know. This happened in our life. It seems like it happened in lifetime. So that one may also know.
Okay, fair enough.
Maybe we'll surprise you.
Manuel, thank you so much. This was
Thank you.